Okay, so this will be our last day sort of in hands-on in Discover. So if you've been trying it, experimenting, running into any issues, please feel free to stop me as I go. If you see something and say, oh, that wasn't working or whatever, um, let me know and we can discuss it. Okay, great. Oh, one more thing I should point out before we get started is if you are encountering any issues with uh, Discover itself, you can, of course, email me, but the best way to communicate an issue with the Discover program is to actually go back into GitHub where you downloaded it. And GitHub supports a kind of issues tracking feature as well. If you go under issues here, it's going to have a collection of like known bugs and defects and features to implement. So I use this myself to keep track of things I find as bugs or want to implement. See here, these are all posted by me. But you can also go in yourself, make an account, and post an issue. And this is kind of supporting the open source software development kind of mentality where, even if you're not involved with writing the code yourself, you can still be involved with the development process by raising issues and suggesting features and things like that. So I would really appreciate that. That would kind of streamline for me. If you find bugs with other things like Docker or Python, just go ahead and email me and we'll try to resolve it. And sometimes I know you're not sure if it's a discovery issue or whatever, so just email me and I'll figure it out. If it does become a discovery issue, then we'll post it here. This is also a good place to go. If you do have an issue, you can see is it already a known issue. For example, I'll mention this today. I found this bug last week. I haven't fixed it yet. It will be, but just so you're aware of it. There's a bug with renaming the variables, and then there's a kind of workaround for the time being. To make it work before the issue is fixed. And then you can also write comments here, say, oh, this works for me. Okay. So let's get started with some examples. I want to just show you 2 examples today, but in a little bit more depth. We're going to go back to our bridge example. And I'm going to show you a little bit how that model works, and then we're going to implement it in both an unconstrained way and then adding a constraint. So I'm going to really focus today on that constraint handling feature and when it can be useful for different design spaces to express a certain goal as either an objective or a constraint. And then I'll show you a second example, which is going to use a kind of branching model to create a structure. And we're just going to try to optimize the size of that structure. And then we'll see an unconstrained version again, and then one with constraints, and we'll kind of compare how the two behave. Okay, so to get started, I'm just gonna start from scratch here. I'm gonna go to where I installed my Discover, and then I'll run the Docker implementation. Hopefully it'll work. Still experimenting with Docker. Takes a minute sometimes. So while that's getting booted up, I'm also gonna launch Rhino and open up my first demo model, which is in the Grasshopper samples folder. Okay, so there's my Rhino. I got my Grasshopper. Oh, by the way, the reason I'm recording this, you might see I'm also wearing headphones. I've been posting these videos on the main Discover page as a kind of temporary documentation. If you ever want to go back to anything we did in class, videos are posted here. Right. Okay, so there's my Grasshopper. Just keep docking things over here. And I'm going to bring in my bridge. You see here, there's bridge and branching. These are the 2 demos we'll do. And there's a constrained and unconstrained version of each one. So drag and bridge here. Okay, finally I decided to start. I'm not sure why it's taking a while now. Troubleshooting this Docker thing. Okay, so here's my bridge model. It's already set up for Discover. It's got all the connections for connecting to the server, the inputs, the outputs. So until we get Discover kind of set up with the proper input set, this isn't going to work, right? So as always, it's helpful to use these Galapagos um, gene pools to simulate the input parameters we want. So if you remember this bridge example, let me get a better view here. It's modeling a bridge based on two sets of parameters. So first, a continuous set of 6 parameters. So let's just model this quickly. I'll talk through it. So there's 6 continuous parameters ranging from 0 to 5. I think it's a weird scale. It's in millimeters, but it's just a kind of model. So here they are. And then, so we connect those to this part of the model, and that will create the heights of our bridge structure. So we have 6 structural segments, and these parameters control the height of those segments. So using the gene pool, we can create a kind of random mix to test the model, or flux the model, it's usually called. And then we have another set of inputs for each of the 5 bays that result from that division. We have a type of structure that can be implemented. Okay, so there's Discover, it's launched. It's ready to go. I'm going to make another gene pool. So here we'll have 5 input parameters, and they're going to be categorical. So in the gene pool, we can just slide the decimal over to 0 to get an integer. And then we're only going to have 4 different types of structure. So we want the integer value to be from 0 to 3, right? 0, 1, 2, 3 will represent our 4 types of structural infill. And that one we will connect here into types. So you see more structure appearing. And now if we shuffle this, you'll see the different structural types. There's 2 types of diagonal bars, nothing, and then X cross brace. Okay, so that's our model. And then it gets put through the structural analysis, which you can look at on Medium for more details about that. It's a pretty basic structural analysis, just converting lines to beams, giving them a basic cross-section here, and then applying a set of loads and constraints or supports for the model. Okay, so let's get this going with Discover. One thing I should say, in the first case, before we look at the constraint case, we're looking at no constraints, purely objective-driven optimization. So I have here 2 objectives that I'm looking at, which are typical objectives in structural simulation, which is the displacement and the amount of material. Typically in structural analysis, as a kind of very basic lightweighting approach, you're looking for the lightest structure. So here material and weight are directly related. You're looking for the lightest structure, the one that uses the least material, which has the best structural performance. And so we have one objective representing the lightness or the amount of material, which can also equate to the cost often. And the other one, which represents structural performance, which is the displacement. And the displacement is a measure of how far the structure moves under load. So it's a kind of measure of stiffness, right? And basically measures the displacement, the movement from the starting position to the final position under load of the node with the highest movement. Right? So it takes the node that moves the most and tells you how much it displaces. So those are the 2 basic criteria we're going to start with. And we're going to try to optimize this bridge structure to basically give us the best trade-off between those 2 values. And remember, with any optimization with more than one objective, we're not necessarily going to have a single best design. We're probably going to get some bridge structures that are very light, but not so strong, or not so stiff, to be more specific. We're going to get some heavier structures, which are more stiff. Okay? So that's the basic setup of our model. We have the 2 objectives connected to the Discover output node. Right, so here's our server. Everything looks good now. I'm going to go back to the browser, and let's set up the basic input parameters. So I know I need 2 sets of parameters, one continuous and one categorical. So I'm going to click the Add Input button here. And I also know I have 2 outputs for my displacement and material. And both are objectives and both should be minimized. So I can keep all these defaults in this case. The bug I mentioned earlier, which will be fixed soon, so it's probably not even worth mentioning. But for the time being, there's a bug that if you try to rename any of these inputs, if you try to then add or delete input sets, things get messed up. The proper kind of sub options don't show up for whatever reason. So the best thing to do for now is to add all your inputs and specify them the way you need them, and then rename them if you want all at once at the end. So that's what I'll do in this case. Okay, so my first input is continuous. The length is 6, right? I need 6 input parameters, and they're going to vary between 0 and 5 units. That's a continuous parameter varying within that range. The second parameter type is categorical. So I'm going to switch to categorical. And the length is the number of parameters, that's 5. I have 5 structural base, and the number of options is 4. So I leave that as it is. So now everything should be set up. I can click test, so I need to connect it to my Grasshopper model first. Go back and just hit that button to make the connection. You can see here it'll connect to the file, and this is where it gets the file name. So that's an important step. It creates a unique connection to that file so that if you have other Grasshopper files open, it's only going to talk to that one, and it even knows its name, and it's going to use that to name your optimization. So nothing really happens until that unique bond is created. Okay, so now I'll click test, and basically just watch for if my model is being updated with those parameters. Okay, so it's not, we know why, right? Because we're using these gene pools to test it now. So now that we have some inputs coming in, we should see them coming out here. These are coming from Discover. And I'm just going to reconnect it to my Discover model and leave these gene pools to the side. Okay, so there's my model. And now if I hit test, it should be updating. So once we know the inputs work and everything's connected with the start button, with the test button, I'm just going to run a really quick optimization to make sure the outputs are connected as well. So Discover will default to this very small optimization, and usually I just like to keep it there and hit start as soon as everything's connected. And it'll run through this very fast optimization. It's going to do 2 things for you. One is you can click load data, and it's going to load up the results, and it's not going to be much, but it's going to allow you to make sure that the objectives are working properly, because we already tested the inputs, but now we need to make sure the outputs are working properly as well. So here you can see our 2 minimization criteria. I should probably rename these before we run it again to be more descriptive. So we can see it's working. The other thing it's going to do for you is open up this floating viewport, which Discover uses to capture the actual screenshots. So for the time being, this whole generation of the floating viewport is automated. You can go into some of the code in these nodes and change the size and things of that viewport. But it's going to launch it when you start the optimization. So you kind of have to like run it once to get the viewport, and then you can adjust your view. You can do this on the fly as it's optimizing. But usually I just like to run a quick test, get my viewport, and then I can sort of arrange the view I want. And this is exactly what's going to be captured in the screenshots. Now, the floating viewport will be 3D to start. Usually that's fine, right? If you're working with this kind of 2D problem, you can just arrange the camera to approximate the view you want. This grid and everything should go away. You can hit F7 and make it disappear. So that's pretty good, you know. But if I wanted like a really straight on view, I can also go here and directly choose the view I want. So here I want the right view. But when I do that, you'll notice that the name of the viewport is going to change from Discover to Right. Okay, so that's the view I want. But if I keep it like this, what happens is Discover looks for a floating viewport named Discover, and if it doesn't exist, it's going to make one. So if I keep it like this, it's going to remake that view and give it that default 3D view. So a quick kind of hack to make this work is just to go to, you know, once you have your view, right, and go to Name Views, and just save this view and call it Discover. And now the label is back. So basically, we just renamed the viewport back to Discover, and now it will kind of recognize them when we run it. And this is a quick way also without getting into the code that you can start to manipulate the view. You can resize it, do whatever you want with it. For example, if you want a higher res screenshot, you should definitely make it bigger. This is optimized for smaller file sizes. So if you really want those nice uh, high resolution graphics for the presentation, then you can make that bigger. As long as it's called Discover, it'll work. Okay, so now that I have my view set up, I'm gonna go back here. I'm gonna rename my outputs. It's more clear. The first one is our displacement. It's being minimized, and the second one is material. It's also being minimized. And then now I can ramp up these numbers to get a larger optimization. And at this point, if I'm testing 20 designs per generation, maybe I want about, I don't know, two to five elites being saved. I'll just leave it here. Yeah. So out of 20 designs, the first 3 will always be the top designs from the generation before. I'll click start. Yes. Yeah. So this is usually done experimentally. It's hard to say for sure what a good mutation rate is. It really depends on the nature of the problem. A good starting point is 5%, which is what the default will be. So it's 5% of designs will get mutated, and within that, like 5% of the input parameters will get mutated. From there, you can adjust it either lower or higher based on the results you see during the optimization. So I would always start with 5%. That's what I typically do. And then basically, you look at the results and then you adjust. And so some intuition for that is basically if you run the optimization and you're not getting enough variation, so how do we know if we're not getting enough variation? We might see convergence too quickly on a design that seems to us intuitively to be suboptimal. You're never going to really know, right? That's the whole point of using these tools. You don't know what the optimal design is. But you might see that like within a few generations, it converges on something like it stops exploring other options and it really just fixates on this design that looks not that great. So then say, okay, we're not getting enough variation. And the 2 causes might be that we don't have enough designs per generation, that the gene pool is actually very limited because all the information about the design space is only stored in each generation, right? Or it could be that the mutation is not high enough, right? Because even if you have a lot of designs, if you get stuck with a certain set of parameters across those designs, it doesn't matter if you have 50 or 100 designs per generation, they're all sharing the same parameters. You might actually need the mutation rate to just force more and more variation in each generation, right? So then you would boost your mutation rate, and then you would hopefully see more exploration at the expense of convergence, right? So that's the other signal that you might see is when do you know that your mutation rate is too high and needs to be reduced? You see a kind of explosion of the optimization, kind of anti-convergence. Instead of seeing that nice trend towards better and better performance, you might see actually the opposite. You might see too much variation, too much divergence. And that might be because the mutation rate is so high that it can't actually fix it on some kind of trend of performance, right? So each time it takes the parents and crossbreeds them, there's so much chance of mutation that that crossbreeding doesn't really create the kind of optimal set of parameters. So really, it's just done experimentally. Okay. So the optimization is running. And in order to see the results, because this is another kind of issue for the time being, that if you rename these outputs, when you hit load data here, it keeps these the same and it won't load up our new names. So I'm just gonna copy and paste the name of our job here, and I could just hit restart. It'll just reload the front end interface and hit paste here and load the data. Now you notice that I've reloaded the window, right, and the optimization is still running because all the optimization is being scheduled by the server. This is just the front end kind of interface. So even if you reload here, the optimization will still keep running, and you'll see here updates about like starting next generation. So you shouldn't be too worried about like closing this window or restarting it. It won't affect the server itself. The only thing is you lose your input and output definitions here. But otherwise, it won't affect anything. So now I can load the data and see the results. Okay, and this is something typical, a typical kind of plot you would see right away from a two-objective optimization. So any kind of structural analysis, you'll usually see something like this. So what we see is our two structural characteristics plotted on the X and Y axis. So this is displacement in millimeters, and this is the mass, right? The amount of material and structure. If we go to isolate optimal, we should see that nice Pareto frontier as well, as the designs try to get closer and closer to this optimal point. And what we should also see is that more later designs in later generations should be getting closer and closer to that Pareto front. Right, so in our case, size and color is representing when the design came in the optimization process. So the more red the design, and later it should start pushing towards that frontier. So in terms of the mutation rate discussion, again, if you can analyze this kind of chart to see if you have the right settings, because you should see that kind of trend of the red designs toward that red front. If you're seeing red designs out here, like too many of them, of course you always get some because we want that kind of stochastic process. But if you see it, designs moving in the wrong direction, right, more and more red like out here, then it might be too much variation happening, too much variation. So we can see that. And what I'm looking for always here is that I'm always trying to get a few red designs in this optimal set, right? So when I'm looking at the design as it's running, I'll keep this isolate optimal on, and I'll keep updating it like every generation or so, every few generations that it's running, just as I'm testing it. Make sure that I have late designs popping up here. So discover, when you hit isolate optimal, it'll show you the earliest version of that design. So if there's an optimal design, it might keep repeating these, but it'll only show you the first generation that design was in. And when you see like all the optimal designs being, more green and blue, it means that new better designs aren't being found. So you're not actually doing better. And that might mean either you found the best designs already, so you're kind of done, or it might mean that you're converging too early. So this is the kind of recurring pattern in this process is there's a lot of times where you're not really sure. You have to really use your intuition again and sort of explore different variations. So if I'm not seeing more and more optimization, I might say, well, maybe my implementation rate is too high, or I need more designs per generation. Start exploring a wider range of the design space. Okay, so as we go, we see sort of, every generation, one or two designs red, so, it's still optimizing. So this will tell me, okay, I need to keep going. I need to keep the optimization running. It hasn't stopped optimizing yet. Okay, so let's take a look at some of the designs and see if it matches our intuition. So here we see the Pareto front. This is a collection of optimal designs trading off between mass and displacement. So if we go here to the bottom end of the x-axis and we start to look at these designs, we see basically our optimal designs that are optimizing the most for displacement. So these are the designs that are the least flexible, right? They're the strongest. And you see there's a lot of structure, right? And it's starting to take more or less a kind of intuitive bow shape that we know is the optimal solution for this bridge problem. And as we scroll down through the Pareto front, we basically see, we can scroll here on the x-axis, get a better picture of that. You can see that trade-off sort of starting to go the other way, right? So as we go further on the on the x-axis, start to see designs that get less and less stiff incrementally, but start to drop in weight. So this design is almost 40% lighter than the first one, but it displaces about twice as much, right? We zoom out here, we can sort of look a bit more at the trade-off. So as we go down here, we get lighter and lighter designs. We can see that displacement getting larger and larger, that movement of the structure under load. So within the definitions of this multi-objective problem, these are all optimal designs. So from here, it's really up to us to choose what the right trade-off is, right? So we might at this point say, okay, this is great, but we really don't want to look at anything with a displacement higher than, say, 0.002. At this point, we might create a cutoff here, and then almost, in a way, make it into a single objective problem by just treating one of the objectives as a constraint, right? So we haven't implemented the constraint in Discover, but we're kind of implementing it on the back end as we're filtering design and say, okay, we said we want to minimize both, but really we want to minimize both while making sure that displacement isn't higher than 0.002. So we only look at these designs. And now that we've established that threshold, it becomes a single objective problem again, right? Because now we're saying, well, as long as it doesn't displace more than 0.002, we're fine, which means all these designs are fine. And then we just choose the one with the smallest value in the other objective, right? Because if we know all these designs are okay, then we know that this is the best design so far, right? This is the one that's the lightest that meets our need. This is the way too that we can already start talking about objectives and constraints, even though we haven't really implemented them as part of the optimization. And now, as we look at this, we might see some limitations. Like, for example, we know intuitively that we don't want anything above 0.002. But Discover doesn't know that, right? So it can easily start to target or converge on parts of the design space that are not interesting to us. But given the criteria we set out for it, it doesn't really know, right? It might, for it seems like it's going in the right direction. So for example, this design here might not be suitable for us, right? But to the optimization algorithm, it seems like a good solution because it's really minimizing that first way objective, or the material objective. Right, so this is where constraints start to become really useful, not just as a post-processing function, but as part of the optimization itself. So we can now actually tell Discover concretely, yes, optimize these set of parameters, but at the same time, make sure that these criteria are being met. So we can start to specify those criteria through the constraints. And furthermore, in this example, I have another problem, because in the typical structural analysis, the first two objectives I mentioned, weight and displacement, are really important. Those are typically used as objectives. There's another really important criteria, which is stress, right? And the problem with this model right now is that we're not accounting for stress, which is why we're getting these designs that to the algorithm seem very good, but wouldn't work in the real world, because these designs, they might have a pretty good weight and pretty good stiffness, but we have no idea what's happening about the stress. In the real world, all three are really important, because you might have actually a theoretically stiff structure, which when the load is actually applied, the stress goes beyond the limitations of the material. And with this kind of linear structural analysis, it's not going to tell you anything about the point where the material actually starts to break apart, but it will tell you how much the stresses are. So typically what we do is we treat the stress as a constraint to say that we want to optimize for the lightest structure, the stiffest structure, but we also want to make sure that no part of the structure exceeds the structural limitations of that material. So what we're going to do next is actually implement that stress criteria as a constraint in our optimization and see how that starts to change the types of designs that are produced. And hopefully it's going to start to produce more realistic designs. Okay, so I'm going to go back here. I think my job has finished. So we'll leave that alone. And in the samples data, I'm going to upload to Dropbox these zip files, which have test runs of these test models. And there's the bridge one, which actually runs through like 50 designs, 50 generations, a much bigger set that you can explore. Okay, so I'm going to go back to Grasshopper, and I'm going to open the bridge constraint file. Here's that model. And it's the same exact model, except I've added a couple components here to measure that stress constraint. And on Medium, you can read about how to extract the utilization or a measure of or how much, what's the maximum utilization of any part of the structure, which is basically the stress that it sees versus the stress that its maximum kind of stress capacity. So when we see a utilization of 64, it means that the member in our bridge, which has the most stress in it, that stress is 64% of its capacity, right? And so when we start to think about that as a goal for optimization, we can think first, do we want to implement that as an objective or as a constraint? And so we could implement it as an objective and basically decrease the maximum stress in the structure. But usually when we think about structures, that doesn't really make much sense because stress is a natural product of a structure, right? We actually want a structure to take on stress. That's what a structure is supposed to do as it carries the load to between the load point and the support. So we don't really want to minimize stress. That doesn't really make intuitive sense. But we do want to ensure that the stress isn't so big that it breaks our structure. That's why typically stress is considered constraint. And we establish the criteria of that constraint based on the safety factor we want to use. Right? So here, if it's telling us that the maximum stress in the structure is 64% of the maximum, that's related somehow to our safety factor. And the safety factor is basically the multiple of utilization that we're comfortable optimizing towards. So if we say, okay, we don't want the structure to break, you say, well, as long as that stays under 100%, then it shouldn't break, right? But remember, we're in a simulation. There's a lot of assumptions happening here. But typically with simulation, we never optimize for 100% capacity. We usually do a multiplier. So if safety factor of 2 means we're actually optimizing for half of the capacity. Right? So even if there's a kind of small error in the simulation or something's not quite right, we're pretty sure that it's not going to result in the structure breaking. Right? So if we want to optimize for a safety factor of 2, we would limit that maximum utilization to 50%. Right? So say that a successful design is any design where none of the members are more than 50% loaded. Does that make sense? And your safety factor typically depends on your context, like how predictable or unpredictable the simulation is versus real life. So I think with engineering applications, like a 2.0 safety factor is typical, but with buildings, it's something much higher, a much higher multiple safety factor. So there's a lot of kind of aspects of the building structure that are really hard to predict in real life. All right, so now that we have the stress being measured here, we're plugging that into the outputs in Discover. So now we have to specify the type of output it is. I'm going to go back to Discover here. I'll just reload it. I'm going to re-input my inputs. So I have a 6 continuous inputs, 0 to 5, categorical input with 5 values, 4 options. I'll bring back my 2 outputs. I'll add a third output, and now I'm going to create a constraint output. And my requirement will be less than 50, right? So I want to optimize for that 50% utilization. So with constraints, you have 3 options: less than, equals, or greater than, based on what you want to do. All right. So let me go back here, make sure my model is connected. So it's loaded in the right name. I'll test a couple times to make sure it's updating. I'll run this small optimization. Now we can hit load data. We'll see what we're producing. So you see something different now, right? You see these little boxes, not the circles. What the boxes represent is basically designs that don't meet that criteria. These are failed designs, or what we call non-viable designs. So in Discover, those are represented in these small boxes. You'll still get the color parameter, but not the size. But we still can see where they are in the design space. Right? These are failed designs, but they're still being measured according to their objectives. And you'll notice in the axis selection here, the constraint isn't there. Right? We're just looking at our objective outputs. This is something I might change in the future, but for now, the idea is we're not really that interested in the value of that constraint. We're just interested in whether it meets it or not. Right? So we're still only really interested in optimizing these two objectives, but subject to those constraints. Right? And in this case, we ran the really short optimization, and it wasn't actually able to find any feasible designs. Right? All the designs break that stress constraint. This is typical, and at this point, we have to decide whether our model is over-constrained. Because it could be that the model is set up in a way that it's impossible to meet that constraint. We don't know. If we're dealing with a real-world problem, like a structures problem, that would be really important, right? We wouldn't want to adjust the constraint if we're really looking for that safety factor. We would need to change the model somehow, increase the size of the beams, or something like that. So let's try that really quick. So I'm not going to change the goal of 50%. You can see here the kind of numbers we're looking at. But I'm just going to go in here and change the cross section to be bigger. So I'll try like 5. So that's kind of dropping. So now I'm just seeing like, okay, maybe now we can start to meet that requirement. And I'm going to apply this actually to all my elements. Right. So now that's pretty low, so I can adjust it from there. All right. So now that we've adjusted the sizes, I'll hit start again. We'll see if we start to get more feasible results. Okay. Now we see a more even mix, right? Even the first generation, we see the blue designs here. It's created a few designs that broke that constraint. So again, stress is different from the displacement and the weight, right? This might be a good design for the weight. We have some concentrations of stress there that will cause the model to break. So we don't want to explore those. And as the optimization goes, what you should see a movement away from non-feasible designs towards feasible designs. Because remember the criteria we're using to evaluate the performance of these things, we consider the feasibility first, right? So if we have all unfeasible designs, it will use those to evolve, but as soon as it finds these feasible ones, it's always going to prefer those over the unfeasible ones. So we should see this movement very quickly towards feasibility within a few generations. Okay. And now just to finish up with this model, we can take a look at a run I did earlier, which is included in those samples. Okay, and this is what, this is a much bigger run. I think it's something like 50 by 50, looking at that constrained bridge problem. And I actually started with a setup that was a little bit harder to meet. So in this case, a lot of the early designs were unfeasible. You can see that even later here, you still have some unfeasible designs being generated at the kind of frontier, right? As it's trying to explore the best trade-offs, also pushing against that constraint. So you will see later designs being unfeasible, but they should be closer to the parallel front than the ones out here. So out here you see some really bad designs, as we move in. Here we can click isolate optimal. You should start to see some designs that not only show that trade-off, between weight and displacement, but also start to be more and more realistic in terms of the design, because these are designs that not only optimize for those two objectives, but also maintain a good stress distribution. And it's something that if you compare the two results, without the constraint, you might get better weights and stiffnesses, but they won't be realistic because they're not distributing that stress evenly throughout the structure. Any questions about the bridge? Cool. All right, so let me show you the second model. We don't have too much time remaining, so I'm going to go through it a little bit quickly. But I just want to show you another example of dealing with constraints, and this time with a slightly different type of model. I'm going to go back to my samples and load in the branching sample. And this is the model based on the example shown in a medium. Basically takes in a set of inputs. It takes in a set of Boolean inputs, 0, 1, or 2, or categorical, I mean. And based on that 0, 1, or 2, it creates this sort of branching structure. And we do that through a piece of Python code. This is a recursive algorithm, very similar to what was shown in Medium. And you can see the behavior here through this, through these conditionals within this single grow function. And then we create the branching by calling that grow function recursively. So we start with a single point at the origin, and then based on these inputs, we make a decision. So if the first input is 0, then we have here basically, if it's 0, nothing happens. If the first parameter is 1, down here, it just grows 1 unit in the z direction. And if the parameter is 2, then we actually grow twice, right? We have m negative 1, 1. That creates a point negative 1 and positive 1 in the y direction. And for each one of those, it calls the grow function 1 time. So within that whole process, like every time there's a 2 parameter, it creates 2 splits and actually recursively calls that function twice. And here, it's popping the parameter off of the list, right? And then with this conditional, once it runs out of parameters, it basically doesn't do anything. So in this case, it'll sort of branch. As long as it has parameters, it'll keep kind of growing from its branches, and then it'll stop when it runs out of parameters. Okay? So it's kind of basic recursive logic. Branching, here we're creating structure, but you can use the same kind of logic to actually start to subdivide structures or do any other kind of recursive repeating process. Okay, so we have these structures that can be created by random sets of parameters. See here from the top view. Kind of, yeah, let me change it to a 3D view so you can see it better. Right? And now what we want to do is basically see if we can optimize the code or this sort of like set of instructions for this recursive algorithm such that the structure does what we want. And in this case, what we want is just something very simple. I want to create the biggest possible structure. All right, so I have my model set up. Let me just reload Discover and we'll set up the inputs and outputs. And go back to Grasshopper. I'll hit the connect button so it connects to the proper file. And I'll create one input, which is categorical with 3 options. And here I can set the length of my input code to just match the sort of potential size of the structure, right? Because once we run out of parameters, the structure will stop growing. So this will basically dictate like how big can the structure possibly get, although we don't really know how big it can get from the beginning, right? That's why we want to optimize it. So here I'm just going to set it to 25 and sort of see what happens. And I can always increase this if I want to make bigger structures. And for the outputs, let's go back to our model and we'll see what I'm outputting. So the results of the Python code are the branches themselves. And what I'm doing is extracting the endpoints from the lines of the branches. I'm getting rid of any duplicates. And then I'm looking here, deconstructing each point, looking at the X, Y, Z um, the XYZ coordinate, and I'm using the bounds component to basically see the minimum and the maximum for each coordinate. So I'm looking at the minimum and the maximum X value, Y value, and Z value of the structure. I'm subtracting the minimum from the maximum. This gives me the range of values. And then here the absolute value to make it positive. So these three outputs are basically telling me how big the structure is in each dimension, how wide it is in both directions, and how tall it is. Right? So these are the two widths. So this one here is 2 units wide by 2 units wide and 3.5 units tall. I'm plugging all of those as outputs into my send outputs component. So I need to specify those outputs here, and these should all be objectives, and this time I want to maximize all of them. So I want to just maximize the total size of my structure, and here we have trade-offs again. Some might be very wide and short, some might be skinny and tall. All right, so let's just test those inputs, make sure everything's connected. So we want to go back here and reconnect the inputs coming from Discover into our model. Let's just make sure we can create some kind of structures. There's going to be a lot which are basically nothing. Like if the first parameter encounters a 0, it's going to stop growing, right? Because that recursive function is never going to be called. Okay. And now let's start the optimization, just to make sure everything's working. Okay, we have a small optimization, but we can see basically, I'll make this bigger. We can see our designs in terms of our objectives. So I have X and Y being the width and the height. I can set the color to be the other width. And then we go to isolate optimal, and we see we have really one optimal design so far. So in this case, even though we have multiple objectives, there is a design because it's just the branching kind of logic that is the optimal design for all of those objectives. It's the widest and also the tallest. And that might change, as we go. But that's the whole point of running the optimization. Right now we can see the sort of trade-offs that happen, and we also kind of have a way to create this non-direct relationship between the input parameters, which are just creating kind of instructions, and then the output, the phenotype of the actual structure itself. All right, so we can run this for longer, but I'm just going to load up a optimization I ran earlier for the branching. So this will be a zip file also uploaded. Let's start. Okay, so this is what we see at the end. We have the two widths, the height, right? You can see how discretized now the objective space is of this model, right? Because as I'm growing the branching, it's very specific. Like I'm always growing 1 unit up or 1 unit to the left and right. But if I'm looking at the width versus the height, it's really discretized into these kind of areas, right? Where here there might be like lots and lots of designs stacked up here, which have width of 4 and 4, right? And a height of whatever this is. Actually, it's a height of 4, the width of 4, and here the color represents the other width. So it can be a little hard to read this, right? I mean, we can still sort of go to isolate optimal, and it sort of fades away some of the other designs, but in a design space like this, there's so many ways for it to get 0, like there's hundreds of designs probably stacked up, that even with isolate optimal, the ghosted things will be pretty dark, but we still see the kind of concentration of designs up here. Now, with a model like this that's very discrete in the outputs, it could be hard to read. So I often like to actually look at the trend over time. So I've shifted the x-axis to ID, and now we can see sort of where those good designs occurred. In this case, the best designs were actually found pretty early in the optimization process. You see here, the optimal design was actually around design 900, right? Even if we ran it longer, like we kept exploring those designs, we could never get something substantially better. Okay, let me show you one more thing. And we're basically going to take this model and add a constraint. So we have a model of branching. We're optimizing the parameters to create the kind of branching structure that maximizes the size of the structure. Let's say now we want to add a constraint in which we want the structure to grow but avoid some obstacle. So I'm going to load up our last example. The branching constraint. What I've done here is I've just added a couple nodes down here. I've created a sphere, 3 units up and 0.9 in radius. And that sphere is going to collide with my structure. So I want to say now I want the biggest structure, so the same exact objectives, but I want to make sure that none of the structure is within that sphere. And to do that really quickly, I just take all the points and I use the brep inclusion component to check if each point is within the sphere. And I use that to basically count those inclusions. So whenever there's an inclusion that's true, if I sum them up, the trues become ones. And so here I have as an output the number of points that are within the sphere. So here I have 2 points within the sphere, and I'm just passing that as an output to Discover. I'm also doing some visualization here to just draw those collision points as red dots, and then also preview the sphere as semi-transparent. Okay, so now my model is set up. I have the criteria I want to use the constraint being sent to Discover, but I actually need to specify that this is a constraint through the specification here. So I'm going to put in my inputs again. So 25 categorical inputs, 0, 1, or 2. I'm going to add my outputs. So these are my width and height. And I'll add another output for the constraint. I'm going to select constraint. And this time I want to say I don't want any points within the sphere. So this value that's coming in as my fourth output, I want to constrain it to not be less than or greater than some number, but I want it to be exactly equal to 0. So my constraint here is equal 0. Does that make sense? So let me test it a couple times to make sure everything is connected. All right, so we see our model. You see every time the model enters the sphere, we get the collisions. So let's run a short optimization. We'll load that up. Okay, and so now we see, after just a couple of generations, that we have this kind of divide between the feasible designs, which are all pretty bad, right? They're all just like 1 unit high, no width, single structure. And we see these other structures, which are much bigger, they're taller, they're wider, they're meeting our objectives better, but they break that constraint. If we go isolate optimal, it's never going to consider those unfeasible designs. It's just going to give us the best design that works, that doesn't touch that sphere. And so our hope here is that the optimization starts to close that gap a little bit. It starts to push the designs to be better and better according to the objectives, but then steering clear of that boundary when the designs are no longer feasible. Right? Now, just to see what happens if we run that model for longer, I'll just load up example I did earlier. Right, and this is what it looks like. So we see down here the sort of not great designs that don't break the constraints. We see here some designs that get bigger, that break the constraints, but we also see the red designs here explored later, which are trying to do both. right? They're tall structures, they're wide, and they're trying to somehow avoid that sphere. And then again, we can look at the performance over time. So just clicked ID for the x-axis. We go isolate optimal, and we see that the optimal designs can be a little hard to read, but this is a solid circle here. You can zoom in and select it. So that's actually the best design that was found, right? About halfway through the optimization. So there we have it. Any questions about this?